last class period, what we looked at was the electron spin when we put an electron in a magnetic field. And so this picture is illustrating the point. The gyromagnetic ratio, or not gyromagnetic ratio, the magnetic moment is this mu, and it's going to be different for different materials. And we found that the average or the expectation value of the Z component and the X component and the Y components of the spin were different. So here was the end outcome for the expectation value for the X component of the spin when we put an electron in a magnetic field. Here is the expectation value for the Y value. So we have X is cosine, Y is minus sine with the same thing. So if we make a graph, here's X, here's Y, and if we plot these as a function of time, what are we going to see? Let's just start with time equals 0. What's the value of cosine 0 at time equals 0? And what's the value of sine of 0 at time equals 0? So we know that at time equals 0, it's going to be there. Now, as time goes slightly positive, what's happening to the X component? Decreasing. What's happening to the Y component? Since it's a minus sign, it's going negative. And so that means it's going to go something like this. And so what we're going to do is we're going to trace out a circle. And so we say that this is precessing. And in this case, I'd say that's precessing in a clockwise pattern as viewed down the X or Z axis. Because if you have a right-hand coordinate system, you need X cross Y is Z. So the Z axis is coming out of the screen. And so this is precessing about the Z axis. And if you actually use the right-hand rule for the precession, you wrap your fingers the direction it's rotating, your thumb points into it. So we'd actually say it's precessing about the minus Z axis. And what's the frequency of the precession? Well, you can see on the screen. We have sine of gamma B0t. So what's the frequency? Omega is gamma B0. Now, notice I said the frequency. You might have wanted to have it in units of hertz rather than radians per second. So we could have used omega as 2 pi f to solve that f is equal to gamma B0 over 2 pi. And this frequency is called the Larmor frequency, L-A-R-M-O-R, Larmor. And it's the frequency it's going to precess. That frequency depends on gamma, the gyromagnetic ratio, and on B, the strength of the external field. So this is something that chemists take advantage of, as well as medical professionals. Looking at the Z values, the component, the Z direction is constant, just as you would expect, right? You expect it to be constant in the Z direction because we have learned that you can have a constant measurable component in one direction, but not all three. You can't do all three at once. And so we arbitrarily decide the direction we're applying the magnetic field is the measured direction that we can know it. The other two we can't. And so this is the component that's going to be in the direction parallel to the magnetic field. And this is the total magnetic moment, which is always the case. So the utility here, notice Larmor frequency omega is gamma B0, is the frequency which it precesses. So we use this in something like a nuclear magnetic resonance. You take a system and you put it in a strong magnetic field. Why do you want a strong magnetic field? Okay. If you increase the magnetic field, you increase the rate at which it's precessing and you're also going to make a bigger energy difference between the up and the down states. So they put it in a strong magnetic field, so they're going to have an easier to read and interpret data. You'll spread things out when you look at the spectra. And then, based on the magnetic field and the gyromagnetic ratio of what you're looking at, so if you're looking at, for instance, let's say you're looking at individual protons gyromagnetic ratio, that would be a different gamma, and thus a different Larmor frequency. So you can actually look at different things by using different frequencies. And so you choose your frequency so that you are putting in an electromagnetic wave that is in the XY plane. Why in the XY plane? Because if you have the right frequency, the frequency between the spin up and the spin down, then it can absorb that frequency. And you can flip the spin. And then they look at the, I think it is the actual, the emission when it drops back down is what they're looking at in an NMR. But that's what they're actually looking at. They're looking at absorbing energy from that electromagnetic wave to make it so it jumps to the higher state and then it falls back down. So let's see if this matches what I said. Creates a Larmor frequency for the nucleus of an atom that depends on the gyromagnetic ratio of the nucleons. And notice you have to have a spin of the nucleus that's not zero. If the spin of the nucleus is zero, well, then it's not going to work. Yes, because if you have two protons and two neutrons, that would be helionucleus. Then you're going to have the spins for the protons like that. The neutrons, they are going to have a net spin of zero.
So if you have something with an even number of protons and neutrons, you need the spin of zero.
Yeah. Okay. Cause the magnum, yeah. So that's what I said. The Stern-Gerlach experiment, you might remember a long time ago when I accidentally quoted the wrong experiment. A long time ago. Stern-Gerlach is an experiment that explores the spins and the quantized nature. So I also mentioned, without naming it because I was worried I would use the wrong name a couple lectures ago. In this experiment, they have a beam of, I believe, silver atoms that goes into this magnetic region. And this magnetic region does not have a constant magnetic field. It has a gradient. See the dB, dZ. The magnetic field is changing. And because it has a gradient, then you're going to have, when the particles go through, depending on their magnetic orientation, it's going to make them separate. And so if you had magnetic moments that could be in any orientation, you would get this picture on the right. So that's the classical prediction. Classical prediction is I have, the electron's magnetic moment could be any direction like this. And if its direction is like this, well, then it goes here. And if its direction is like this, it goes here. And if its direction is like this, it's, there. And it's just going to vary by how much it's tilted. So the fact that they see only two lines there tells them that you only had two states for the orientation of the spin. And now I said the electron, I would actually have to go back. I'm pretty sure that it's not nuclear spin, but it could be. I didn't review the Stern-Gerlach experiment to make sure which spin it is. But it's showing the quantization of spin, that the orientation can't be anything. Which, if you think about it from the quantum physics, we've gone through this math, sure, it seems logical. But then when you think about, now what am I really saying? I'm saying that I simply can't take the electron, put it in a magnetic field and say, okay, I want you to be oriented like this. It can only be oriented if the magnetic field is vertical like this or like this, no matter what I do. Which it doesn't make sense when you think about it in a physical sense. And that's part of what we deal with in quantum mechanics, as you've well learned, right? So this here is actually showing how you get the calculation for the force. The force is, this is a definition force is equal to minus the gradient of the potential energy. Right, that comes, potential energy, U is defined as the minus the integral of force dot D, and I'll put dr to make it three-dimensional. So since that's the definition of potential, you use the fundamental theorem of calculus. You take the inverse function of the integral, which is the derivative. Since that's three-dimensional, you have to use the gradient and that's where it comes from. And so that's why you need to have a changing magnetic field so that you have that gradient in the potential. So the force is proportional to that gradient. So why am I spending 5 minutes on this or whatever I did? It's a practical experiment that has been done, that's conducted to illustrate what our math says turns out to match reality.
So does this joint Gerlach work with bar magnets? I was watching a video on this and they were saying that it doesn't.
You say work with bar magnets. I'm a little confused
They
with what this
they
means.
were talking about the fact that it precesses and doesn't actually like go up to the north and south pole. That's the reason that it's able to work to measure spin or to like measure where the gradient is.
Well, yes. The fact that we can't make the magnetic moment align in any orientation, that can only be at an angle to, is the reason. But I'm not sure how the bar magnet played into that. Unless it was just saying, if we compare that to the classical world where the bar magnet can have any orientation, right? If the bar magnet can have any orientation, then you get the one that's filled in black, the classical result.
Yeah, I mean that's what would make sense to me. Like, is that having the bar magnet like just go and be attracted to one pole or the other? And because those are both magnetic poles, right? The north and the south on the apparatus.
This here,
Yeah.
yes.
So if you were to just put a normal magnet, a classical magnet in there, it would,
Instead of this, is that what you're saying?
no, like into
No.
that magnetic field. If you were to put a particle that was a regular magnet,
Mhm.
a classical magnet, it would just attract to one of the poles or the other.
It would orient,
Based on its alignment.
depending on its orientation. If it's oriented like this, it wouldn't move, right? It just goes straight through. If it was oriented like this, it would have a smaller force in the vertical direction, so it'd go up a little bit.
Okay.
Oriented like this, it'd go up a little more. Oriented like this, it'd go up the most. Right, so you would have a continuous range of how much it's deviating depending on the orientation. And of course, if it's in there long enough, sure, it would start going like this, right? It would be twisting if it's in there long enough. So it has to be in there short enough that you don't have it just going like this and that dominates.
Right. Okay.
But yeah, I think when you say bar magnet, you mean just a classical magnet that could have any orientation. And then it gives you a result, but it's not the same result. Okay, now we're going to get into systems with two electrons. Or this could apply if we had two protons or two neutrons. So if we have two electrons, we're going to have the spin state has to do with both of the electrons. In fact, let me back up just a second. I was absolutely clear when I was at your level that when we were studying the hydrogen atom, we were specifically studying the electron, that it was the energy of the electron. If I have one electron, this is its energy. If I have a second electron, this is its energy. In fact, if you were to sit in my general physics class this morning, I spoke just like that, didn't I? That's not the case. The energy state is a shared state between all of the constituents. So in a hydrogen atom, it's an energy state for the proton and electron system. It's not energy that's only owned by the electron. It's energy in the system. And so if I have a helium atom that has two electrons, the energy levels are a little more confused. Now, we're going to start off by saying we just have two indistinguishable spin 1/2 particles. So this could be two electrons bound to a helium nucleus. It could be two protons in a nucleus, but they do need to be indistinguishable. So it can't be one electron bound to one hydrogen and another electron bound to a different hydrogen. Those would be distinguishable. It could be an electron in a hydrogen, an H2 molecule that's shared between the two. Then that would be, if we have two electrons shared between two hydrogen atoms, that's what we have, right? If we have a hydrogen molecule, they're sharing their electrons. So that could be a state where we have this situation. You can't distinguish. You can't say, oh, this electron belongs to atom A and this one belongs to atom B. They're shared. So we're dealing with that. Now keep in mind we have the Pauli exclusion principle that says we can't have any two electrons in the same state. So that's going to come up later on. We'll start off by talking about electrons, ignoring that option. So if I have two electrons, there are four different possible arrangements I can have. I can have two electrons aligned up, two electrons aligned down, the first one up, the second one down, or the first one down, the second one up. Right, those are four different options. But if we talk about the spins, what is my total spin going to be for this first picture? It's going to have a spin of 1. What's the total spin of the last one going to be? What about the two in between? They're both 0. So what we have here is 4 states. We have a 1, and then we have 2 of them at 0, and we have 1 at -1. It's going to take a little bit more complexity to think about this. So when we talk about the spin states, we have different ways. Again, at the bottom, I have chi1, chi2, spinner for electron 1, spinner for electron 2. And then I put in a ket up, up, and a ket up, down. Different ways of indicating the same thing, right? So we'll talk about the Z spin state and the total spin state. And when we add spins, there are two options. They can be aligned or anti-aligned. And the M sub S's, which in this case I just called M, can be the numbers we came up with. So what we calculated was the M values. What about the total spin? What total spin values do you suppose I can have? If each is a spin 1/2, what's the total spin going to be? Well, no, what we calculated, what I called S here, I should have called S sub Z. That was what it was. The total spin, since they're 1/2, there's no negative 1/2 for the total spin, right? They're just spin 1/2 particles because you're talking magnitude. And so the total spin can only be S equals 1 or 0. Now, let's talk about S equals 1 and S equals 0. What M sub S values can I have if M is equal to 1 and if M sub S is equal to 0? Well, if we sum them, if we sum them, or excuse me, not if we sum them, I'm sorry. Just thinking about S as a single thing by itself. If S is 1, it follows the same rules as L. So if L is equal to 1, what values could M sub L have? And if L had been equal to 0, what value can M sub S have? So our S sub Z values are labeled by our M sub S's, right? Because we're going to have S sub Z is equal to H bar M sub S. And so when we labeled these S sub z's, that meant I had m sub s equaled 1 here, m sub s had to equal -1 there, and m sub s was 0 here. These are the m sub s's. Yeah, these I should have put, these up top should have been times h bar. Yes, you're right. Where'd the h bars go? So it's easy to say this here and this here, those have to be 2 of the s equals 1 states. So s equals 1, this must be up, up, and down, down for the m sub s is equal to 1 and -1. But that leaves 2 states with 0, and we had 2 states there with 0. What would you do then? They're kind of hard to differentiate, right? There's a couple ways to go about this, and what we're going to do is say, well, what's the raising and lowering operators? So if I want to calculate, where's the raising and lowering operator? Yeah. If I want to calculate my ladder operators, my S plus is going to be S1 plus S2 plus. My S minus is going to be S1 minus plus S2 minus. And so S plus or minus acting on a spinner gives me this stuff, right? We've seen that before. And so let's just take one that we know is in the, by the way, let me come back here and just mention, oops, here. This here is called the, well, this one here, the top, the S equals 1 is called the triplet state. Triplet state because you have 3 values for m sub s. This one's called the singlet state because you have only 1 value for m sub s. So what kind of state do you have for a regular stationary, or not stationary, isolated electron? How many m sub s values could you have there? 2. So that'd be a doublet state, right? Okay, so that's what we mean by triplet state and singlet state, the m sub s values that can go with your total spin. Yeah, I was on this one. So let's take one of those triplet states, one we know is a triplet state. We know that m sub s equals -1 is down, down. And so that means if I take S plus and have it act on down, down, what am I going to get? By the way, remember this here turned out to always give us 1.
Just be h bar times ket.
Okay, so, oh, I really should have been more careful. This here, this subscript 1 means that it acts on the first one in the ket. This subscript 2 means it acts on the second one in the ket. So if I do the raising on the first one, it's going to give me that, right? I changed the down state to the up state for the first one. And then if I do raising for the second one, what am I going to get? What this means is that I must have gone from my m equals m equals -1 state to my m sub s equals 0 state, except for I have the h bars in. So I do need to normalize this now. So how do I normalize this?
Well, just the equation of the integral over,
We actually can't do integrals because it doesn't have a wave function. You're thinking properly, but we don't have a wave function, so we can't be done as an integral. But I need to have my s equals 1, m sub s equals 0. That needs to be 1. Right, that's the integral thing you were talking about can be written in shorthand like this, and it's still got to be this. So the integral is when you have a wave function you can integrate. But this is going to be correct even when you don't. And so I'll take this whole thing and say, well, I multiply it by some normalization factor A. And so this would be A star H bar so there's my bra, and then for my cat bar, and that needs to be 1. So I will immediately divide by the A star H bar stuff so I don't have on the right hand side. I just put the H bar inside the mod squared to make my life easier. So what do I get when I have this acting on this? Two, that's right. And just to make sure, I'm pretty sure that chat gets it, but just to make sure, these are the same state, so that's going to give me a 1 by orthonormality. These are not the same state, so that's going to give me a 0. These are not the same state, that's going to give me a 0. These are the same state, that's going to give me a 1. And so I have 1 over A h bar mod squared equals 2. Therefore, A h bar is equal to 1 over square root of 2. And so my S equals 0 triplet state I now have as, I'll put them here, triplet states. There's my S equals, or M sub S equals 1. I already had my M sub S equals -1 is down, down. And now we just found my M sub S equals 0 is 1 over square root of 2 times up, down, plus down, up. So there's my triplet states. The middle one is a superposition state. It's a superposition of 2 different states that were what we call degenerate. They both had the same m sub s. But we've now broken that degeneracy just by using a raising operator. What does that leave for our singlet state?
Just that degenerate or non-degenerate.
Well, it needs to be orthogonal to this other one that uses the same 2. So we can't, right? We use both of the ones that gave us m sub s is 0 and we didn't put them in, they came there mathematically. But we have both of them. So now we need to find something that's orthogonal to that, that's still made up of those 2. So now we're going to have, for the singlet state, can you guess what it's going to look like? Basically, we have a vector that is 1, 1, right? We have a normalization constant. What do I need to have for these 2 to make it equal 0? What are we going to have? Yeah, they have to be opposite signs. You're going to have the same normalization constant. So it's going to be 1 over square root 2 up, down, minus down, up. And of course, you could have been down, up, minus up, down. That's fundamentally the same state. So that's our singlet state. Some observations we can make about these states. What happens if I were to exchange particle 1 with particle 2? If it's a triplet state, what happens if I exchange them? Like, let's take the m sub s equals 1. It's up and up. What happens if I flip them? Nothing. The m sub s equals minus 1. Down and down. What happens if I flip them? Nothing. Now the middle one, it's up and down, plus down and up. So what happens if I flip those? They're the same. So we say that these triplet states are symmetric under exchange. They're symmetric because it doesn't matter if you switch the particles. The singlet state, on the other hand, what happens if I switch up, down, minus down, up? If I switch them, what have I done? It's changed the sign, right? So it's anti-symmetric under exchange. So there's a fundamental difference in how they behave with exchange between the 2.
So if you say down, up, minus, up, down, that would be a different state than what we have there. Singlet state.
Well, it's anti-symmetric. I said there's no difference because it's multiplied by minus 1, right? If I take the state and multiply by minus 1, I don't consider it different as a state, but it is anti-symmetric because you've changed the sign of the state. To review, how did we find this state here? How did we go? We started with this state. How did we go to that one? We used the ladder operator. We raised it. So what should happen if I put the raising operator on this state? Should go to the next one. So if I put the raising operator on it, And of course, I'm totally out of space on this slide and the one that I did the original work on. So I probably have it on a coming up slide. I just, you like to do your own work and not just look, here's words. I wrote them earlier. So if we did the raising operator, I'm just going to have to do it. As you can see, yes. Here I showed the raising operator on the down, and we got to this state. And then if you use the raising operator on that state, and so here I didn't even worry about the normalization. I just did the raising operator on it again. Then we're going to have, of course, should have h bar squareds. And I'll do it down here just. I'm changing from the h bar to 1 over root 2 because that was our normalization constant. Remember, the raising operator is going to first raise the first one and then plus raising the second one. So if I raise the first one, I'll do raising the first one in blue. What do I get if I raise this? If I try to raise it when it's already in the up state? 0, that's right. What do I get if I try to raise this? I get up. So I'm going to have 1 over root 2. And then I have the h bar because that comes from each time I do it. And I have up from applying the first one. Now let's raise the second one. What do I get when I raise the second item here? And what do I get when I raise the second item here? Don't need a parenthesis. Then we have to normalize it. And when we normalize it, of course, what's the normalization constant? Well, everything out here has to turn out to be 1. So we have, it raises to the up state. So we can actually see from doing this work that, nope, this is not it. This is where I did. That raising this gave us that, raising this gave us that. And if you had done lowering by the symmetry, you can see it would do the same thing. What about if I raised this one? What happens if I raise that s equals 0, m sub s equals 0? Wait for my body to stop making noises. When I raise the first one, I'm going to have minus up. When I raise the second one, I'm going to have plus up. And so what do I end up with? Okay, so you don't have a raised value for that one, just like theory says should be.
Wait, but the normalization constant I'm still stuck on for the second time.
Okay, so this here?
Yeah.
Well, this here is what we get when we have this raising operator. So it's not giving us just the new function. It's giving us the new function with an eigenvalue. And so we need to normalize this new function. So we just take, a times this stuff. We find that it's equal to 1. We find what a is. Well, I will just find that a 2h bar over square root 2 is equal to 1.
Yeah.
And so I don't find what a is per se. I just, it's got to be normalized, so that has to be 1. So a is going to be, obviously, since 2 root 2 is root 2, a is going to be root 2 or 1 over root 4 h bar. Or no, 1 over root 2 h bar. Anyway.
So when you're writing out those eigenstates, you're not writing out the normalization constant in front of them.
Well,
When you did the M's.
when I do this, there's no normalization constant. When I wrote them, let's see, where did I write them? When I wrote them here, these are the normalized eigenstates.
Okay.
Right, so there's the normalization constant, 1 over root 2, 1 over root 2, 1, 1. So that's what it means to have a singlet and triplet state. So if I have 2 electrons, the 2 electrons can either be in the singlet state, where you have the combined spins they added antisymmetrically, or you can be in the S equals 1 state where they added symmetrically. And if they added antisymmetrically, you have an antisymmetric wave function. If they added symmetrically, you have a symmetric wave function. And so, when they talk about the singlet state and the triplet state, you have your energy based on the combined S value and the combined M sub S values, not on the individual ones. You could calculate them with the individual ones, but you're going to get the same thing for, the singlet state or the triplet state. So that's why we just list them with the singlet state. And yeah, look there. After doing all the work that we've done, there you have it. Now, what is this nomenclature here for the bra and ket? What do we have for the 2 things in there?
M or S.
Yeah. Just want to make sure so you don't think there's some kind of okay, so I've got values in there and I don't know what they are. They, is the first one the first electron, the second one the second electron? No. It's the combined S and the combined M sub S. This is more fun math. How do we construct S squared if we have 2 particles? With 1 particle, S squared is S dot S, and it was pretty simple. With 2 particles, we have, spin is S for particle 1 plus S for particle 2. When I dot those together, I'm going to have S1 squared plus S2 squared plus S1 S2 plus S2 S1. Now, these here, because 1 does not affect 2, you can combine those together. So that will give you 2S1 dot S2. If I remember correctly, I didn't think I'd get this far in my lecture, so my preparation ended with the last slide. Good. I showed myself to be right here. And so if I want to do what the S's are, I have SX1, SX2, SY1, SY2, and SZ1, SZ2. So we have a lot of fun work coming down the pipe on this. We have our operators, so we can do what we can replace these with operators, but we have, if it's 1, it only acts on state 1. If it's 2, it only acts on state 2. So it's going to be somewhat tricky, as you can see. So what is my eigenvalue when I find S squared on the up state? Well, I have S1 squared in the up state, S2 squared in the up state, plus 2 S1, S1x, S2x, plus SY, S1y, S2y, plus S1z, S2z. And so you have to go through and do all of this work. The first two are easy, right? The S squares always give us 3/4 h bar squared as their eigenvalue. But then these here, we have, if we're switching both of the x's, switching both of the y's, switching both of the z's, it comes out, and this here, we haven't shown the work exactly of how these do it. And so that's part of the joy. But it does come out that that these combined together just are the same as that. And I'm not going to spend the time doing it because I may finish in time and I may make a mistake. Like I said, I didn't think we were going to get this far in the lecture, so I didn't prepare to do this. So we'll stop now, 2 minutes early. Any questions as we head into our long weekend again? It's always long weekends for this class.
Can you go over the non-infinite PHYS perturbation briefly?
Oh, the mass?
Yeah. Because I think I understand it, but I don't want to write it.
Okay, so this here, we will just what is happening is instead of having the electron orbit at a distance of r away from a stationary point, you have the electron, the proton orbiting about the center of mass. And so if we have, here's my proton, here's my electron, then the center of mass, I'm going to consider the proton at x equals 0. So it's going to be m1 times 0. These are separated by distance a. So that's my center mass position. So then I'm going to have R1 is equal to x center mass is equal to A times M2 over M1 plus M2. And R2 is equal to A minus x center mass is equal to A minus A M2 over M1 plus M2. Giving ourselves a common denominator that's equal to A times M1 plus M2 minus AM2 over M1 plus M2, or AM1 over M1 plus M2. So now I have the two radii, and I have my orbiting about that. So the easiest way for me to explain further from this is to simply talk about classical physics and then say it's all the same. So in classical physics, we talk about I, the moment of inertia. The moment of inertia is our equivalent to mass for a rotational system. And I is equal to the sum of mass I, Ri squared. So that's equal to M1 times R1 squared plus M2 times R2 squared. So if I replace my R1 and my R2, these are M's on bottom, not R's. So there I've expanded it out. And now I'm just going to factor out what I can. everything has an a squared, everything has an m1, everything has an m2, and then I'm left with the first term had an extra m2, second term had an extra m1. Now I can cancel one of these, and I'm left with this, which is often written as a squared mu, where mu is the reduced mass. Now, all of this to say, what do I have? When I have two items orbiting about their center of mass, I can take the separation between the two, A, and this reduced mass, mu, and treat it as one object orbiting. So this is essentially what we're saying is, okay, so the nucleus is not infinite in mass.
So it's not stationary.
So what I'm going to do is shift my mass just a little bit using this reduced mass to compensate so it's not like some random amount. And now it behaves like I do have, in actuality, an infinite mass, fixed mass that just one object with reduced mass is orbiting about.